Hello, my name is Atakan Topcu, and with my teammates Yağızalp and Kerem, we will demonstrate our realistic magnetic resonance imaging simulator for our medical imaging course. MRI has been a popular modality for recent decades due to its flexible functionality, as it can pick out different features in the image using different modes. And also, it is a non-invasive radiation-free imaging modality. And because of this, we wanted to implement MRI as a MRI simulator and analyze the effect of non-idealities such as chemical shift and B0 inhomogeneity on various reconstructed images. So in this project, we choose T1, T2, and PD as our contrast methods, and also different slice as an added functionality, different slice planes, slice location, and resolution can be chosen. And also different spin and gradient echo sequence can be chosen, and different non-idealities can be applied. So as a data set, we have used the discrete normal brain data set of brain web, and it has 1 millimeter slice thickness. In terms of magnetic field, we have used 1.5 Tesla B0 field, and depending on the user input, a B0 inhomogeneity can be applied as Gaussian noise with zero mean and 4.5 microtesla variance on each voxel, which correspond to 3 ppm inhomogeneity. As for the chemical shift, it occurs due to differences between resonance frequencies of tissues, and it mainly happens around fat-water interface, and it can change V0 and Larmor frequency, which can alter the reconstructed image. And as for the slide selection, we use the following equations, and we also created 3D tensor maps for our T1, T2, and PD mappings. And after our slice is selected, we only extract the 2D matrix of the tensor and squeeze it in order for higher computational efficiency, and circularly shift the slice depending on the user.
In order to acquire data, first we need to acquire a magnetization matrix. First magnetization matrix is the transverse magnetization matrix, and second one is the longitudinal magnetization matrix. The formulas for these matrices can be seen. Then we define a function f of xy from these matrices, which we use to generate the K-space matrix. Here, M0 is our initial magnetization matrix. Then, in order to reconstruct the data, we scan the K-space by line-by-line fashion, and we need to demodulate the K-space data by using the following formula. Here, S of t is the signal. Then, after demodulation, we can adjust the resolution. The resolution can be adjusted by changing the extent of the K-space. Resolution of the and K-space are related with this formula. Then we can use 2D inverse Fourier transform to obtain the image from our signal. Here you can see our echo sequences. On the left-hand side, you can see spin echo, and on the right-hand side, you can see gradient echo sequence. Here we don't send RF pulse. Instead, we generate a map from data sets and use that as a simulation for RF pulse. In this table, you can see the timings for the echo sequences. Most important one is the TE value for T2 star and T2. Here, the T2 star decays much faster than T2, thus TE value chosen as such in the table. Here in the application, you can see the parameters and the output.
So I would like to share our results with you. In the following images, you can see that we have reconstructed using T1 weight and with gradient echo sequence for 3 different planes. And for the next images, we have T2 weighted images for spin echo sequence, and such images are also reconstructed in 3 different planes and also with a different slice selection, as we can select our slices. And for resolution parameter, the best resolution that our simulation provides is 1 millimeter resolution, as you can see in image A. And as the distance increases from 1 millimeter to 8 millimeter, the resolution decreases and the image becomes more blurry. One of the non-idealities that we've dealt was B0 inhomogeneity, and in order to simulate that, we created 3 parts per million variation by applying a Gaussian noise to each voxel with 0 mean and 4.5 microtesla variance. And the results can be seen in this slide. The images without any inhomogeneity can be seen on the left side, the images A and C. And when we add B0 inhomogeneity, such images become the images on the right-hand side, which are images B and D. Another non-ideality was the chemical shift. Even though there is no easily visible difference between images A and B, when chemical shift is applied, when the 2 images are subtracted from each other, we can see that on the interface of water and fat tissue, there is a difference due to chemical shift. Due to chemical shift. And as we've mentioned before, the images are using 3 different weights, namely T1, T2 star, and PD. We can reconstruct the gradient echo images, and such images come up with different colors for different tissues. And for brain tissues, one of the most important, 3 of the most important tissues are gray matter, white matter, and CSF. And in the table, you can see how T1, T2 star, and PD weighted images result in different coloration of reconstruction of the images. For spin echo sequences, T1 contrasting is really similar to gradient echo, and the most significantly different one is T2 contrasting. And the coloration is slightly different for spin echo than gradient echo, and the coloration differences can be seen in this table.
So overall, we showed the effects of the non-idealities by using different weighting methods and different echo sequences. However, the chemical shift was hard to observe, so we took the difference between the ideal image and the chemically shifted image to observe the effect. Also, the reconstruction of the image takes approximately 20 seconds, and we can obtain maximum 1 millimeter per pixel resolution. The project can be improved by reducing the computation time while reconstructing the image and increasing the resolution. Overall, we successfully demonstrated the effects of mentioned non-idealities on different slice planes and slice locations by using different weight modes.
So as for demonstration, this is our created application. You can see that we can choose different slice planes. And as for demonstration, I will choose digital plane. And as for slice, let's say 100 slice, and we will keep the resolution and disable the non-idealities. And for spin echo, PD weighted image will be generated in approximately 20 seconds. As you can see, our images correctly, properly reconstructed. And this was our project. Thank you for listening.
Çok güzel.